It is based on observing the scattered intensity of an X-ray beam hitting a sample as a function of incidence and scattered angle. Incident and scattered angle. X-ray diffraction technique is based on elastic scattering. On elastic scattering, remember this. Uses single crystal X-rays used to solve the complete structure of the crystalline material ranging from simple inorganic solids to complex macromolecular materials, right? When I told you about the small angle X-ray scattering that is used for macro molecular materials such as proteins and many organic materials. Powder X-ray diffraction is used to characterize the crystallographic structure, crystallite size, and I have intentionally written grain size, right? So grain size is wrong. Grain size is measured microscopically with optical microscope, with scanning electron microscope, but you can't measure the grain size with X-ray because it uses the Scherer formula, and that is for crystals, not for grains. A polycrystalline sample and single crystal. Polycrystalline, the polycrystals are the same crystals as the single crystal, but when the size of the crystal is small, they are oriented in different ways, and you see different crystals within the material, and people call it polycrystalline material. And when it is a single sheet, it is a single crystal, right? So polycrystalline doesn't mean necessarily and compulsorily mean that it is a different material. It can be. A second phase may be there in polycrystalline material. But in general, when we are talking with reference to the single crystal and polycrystal, it means that here we have crystals, different crystals at different orientations, and obviously smaller in size in comparison to much smaller in comparison to the single crystal. So powder diffraction is commonly used to identify unknown substances through phase analysis, right? X-ray machine, I don't know, but X-rays are used in electron microscopes to identify the chemistry of the material. When the electrons hit the sample, they shift the electron, excite electrons in the material of the sample, in the atoms of the sample. And when they emit X-ray, those X-rays are then used to know about the elemental composition, not oxide composition. Elemental composition, because the X-rays are coming from atom, and atom is not oxide, right? Atom corresponds to an element. So, you know, and that is why when you say EDS in scanning electron microscopy, and some people call it EDX, right? So it is not EDS or EDX. These names are just to shorten things. It is energy dispersio X-ray electron spectroscopy. Energy dispersio X-ray electron spectroscopy, right? You use electron to generate X-rays from there, and those X-rays are then identified to know the elemental composition of the material. By comparing the diffraction data against a database maintained by the International Center for Diffraction Data, this sentence, powder diffraction is commonly used to identify the unknown substances unknown substances, if you are technically speaking, you are not identifying unknown substances. You are doing phase analysis with X-ray. You are identifying different phases within the sample, and then the phase tell you about the substance, right? So technically you are doing phase analysis, and then when you know about different phases inside the material, then obviously phases have certain chemistry and you know about them. But X-ray tells you not from chemistry in this case, but from the diffraction data, that where the X-rays were diffracted and how the orientation of different planes with respect to one another is, and how much is the interplanar spacing between consecutive planes, right? I'll show you some planes later. We also used to characterize a heterogeneous solid mixture to determine relative abundance of crystalline phases. I have told you that if you have a diffraction pattern like this, and some peaks are coming from one material and the other from other material, then you measure the area under the peak of phase, say alpha, and then the area under the peaks of phase beta, and you know the volume fractions of different phases within the same sample. But when you measure the area like this or like that, it is the raw data. The raw data means how many filters did you use? Someone is using more filters, his data is more refined. Some people are using very slow scanning speed, and some people are using very fast scanning speed. So the intensities will be obviously different. Similarly, the electronics which are transforming your data from digital to analog converting and analog to digital converting, some things are lost or disrupted there as well. So people rely more on the theory in comparison to the experiment. So nowadays, what people do, when you measure something, people theoretically draw their diffraction pattern, that what should happen in the ideal condition, and then subtract the unwanted or the unexpected regions from there. The background, how much background is coming there? Background is part of none. It is neither coming from one phase or from the other phase. It is because of the machine flaw. Similarly, the spreading, if a plane is here and it is directed to this point, right? Then we should have points at this angle to become. Why we are hearing this? This means that we are transforming information and it is spread around that central position. So the angle, which is this, but the peak is coming like this, right? So this spreading is not the characteristic of the sample, but it is of your instrumentation. That what sort of instruments you are using, and they are spreading the beam when they are coming back. When coupled with latest refinement techniques, this is the theory, right? Such as refinement provides structural information of unknown materials. Powder diffraction is also used for determining strains in crystalline materials. Thin film diffraction is used, not are, is used, right, to characterize the crystallographic structure and preferred orientation of substrate anchored thin films. When you are making thin films, then you can determine the orientation of the crystallographic surface, prefer orientation of the material, that along which plane these crystals are there. If you remember when we were talking of heterogeneous nucleation, and I told you that when you want to increase the number of crystals, right? When you want to increase the number of crystals, you need some nucleation agent, right? For example, you used different things to enhance the fermentation of yogurt, of flour, when you are making bread. So you are using various agents there. They accelerate the process of fermentation. Similarly, people use nucleation agents to accelerate the crystal nucleation, not crystal growth, crystal nucleation, the number. And I told you that one of the theory tells that the crystals of the parent phase epitaxially grow over the nucleation agent planes. The planes of the nucleation agent crystal are such that the energy requirements are minimum almost for the parent plane to come and sit upon it. And when that starts, then at every nucleation agent point, a crystal will form there. Instead of, for example, this pen and this brush, it has no harmony. If I am making the crystals of this pen or this brush, I will have to independently struggle and bring only the planes of this brush or the planes of this pen together to grow the crystal or to form the crystal. But if I am forming this crystal and this black has common planes with this blue pen, and I have these planes, then they will easily come to this because of the energy requirements, not because of the color or anything else. Energy requirement will be less and the crystal will preferentially form. For example, if the 111 plane and the 111 plane of the parent and the agent are matching and they feel no difference there, right? Then they easily come together and the crystal will grow over there. So what were we talking about? Yes. So when you are making films and you are making forming thin film over a substrate, you need a specific orientation of the crystals for some other process. And people can easily know from XRD if those preferred orientations are available, and the sample in X-ray will tell you that it is preferred along with which direction. And then along specific direction, uniform properties and directional properties. Many materials have directional properties. For example, you have a crystal, and when you measure the dielectric constant along the 001 plane, it is different in comparison to the 010 or 100. So this means that property is directional, right? So you need that optimum directionality in the sample, and you use X-ray for the thin films to know about along which zone axis is the preferred orientation of the sample. High resolution X-ray is used to characterize thickness, crystallographic structure, strain, and the epitaxial film. The word came again. The epitaxial film. So you have some epitaxial, some base for epitaxial growth of crystals on the top of the sample. X-rays full figure analysis enables one to analyze and determine the distribution of crystalline orientation within a crystalline thin samples. Right? So X-ray is not an imaging machine that people put XRD on their paper or in their presentation and say, I have done XRD of my sample. XRD tells you a lot of science. Right? So think about these things, that how we are using XRD, how can it be used.